Like to repeat three important points what we have observed in a paper and pencil method. The first one is the divisor is repeatedly XORed with part of the dividend. Okay, we are talking regarding XORing of divisor repeatedly with part of the dividend. At every step we are performing that XOR operation. This is the first point. Second point is that the divisor has, say, general thing n minus k plus 1 bits. If it has so many bits, yes, which either are predefined or they will be zeros. In other words, the bits do not change from one data word to another. The third point what we observed in this is that usually if I say my divisor length is n minus k plus 1 bits long, then at every step, okay, only n minus k bits of the divisor are needed. N minus k bits only are needed in the XOR operation, because at every step what we are doing, we are making a MSB bit 0, MSB position of the outcome. Every step we are making MSB position of the outcome should be 0. We are ensuring that at every step. I think it is clear to you. So these are the three important points which we will use in designing our, say, divisor, which will be used in CRC. To start with, you see, so I will design a hardware circuit for a divisor for the previous example. In the previous example, my divisor was 1011. So for that, I am going to design a hardware circuit. So this is what is the hardware circuit what I need for my divisor. So as I said, you need n minus k bits to be XORed. Only n minus k bits of the divisor will be used for XOR operation. That is what I have shown over here. So you see, in this case I have 4 bits in the divisor, that is n minus k plus 1 bits, its length. If it is 4, then n minus k bits means it is 3. Only 3 bits of the divisor will be used in XOR operation. Fine. So then this will be my D0, this will be my D1, this will be my D2. Here I have shown a broken link mainly because no matter whatever may be my quotient value, if it is 1 or if it is 0, this bit, you see, all the time it is 0. Since it is 0, every time it is 0. So that is why I have shown it with a broken link. And the leftmost bit of our dividend will decide these 2 bits. So my leftmost bit which is applied over here, which will going to decide these 2 bits. If the leftmost bit of the dividend, if it is 1, my divisor bits, these 2 bits will going to become 1 1, and this third bit is fixed, it is 0. Yes, look at this. And if it is 1, leftmost bit of my dividend is 1. Just I'll just rewrite that. You see, 1 0 1 1, 0 1 0 1 1. This leftmost bit, if it is 1, my divisor, you see, these 2 bits, you look at these 2 bits, these 2 bits will going to become 1 1. If by chance, if the leftmost bit is 0, you see the rightmost bits, that is D0 and D1, they are zeros. Okay, so this bit, leftmost bit of the dividend, will going to decide the fate of these 2 bits. But whereas this bit value is fixed, it is 0. So if the leftmost bit of the dividend is 1, these 2 bits will going to become 1 1, and if it is 0, these 2 becomes 0. And these zeros will going to be XORed with my this is regarding dividend, they will going to be XORed with the dividends. And you know that every time this position value will going to become 0. So I have not taken this bit into a consideration. No matter whatever may be this value. So we are selecting our dividend in such a fashion that this position outcome all the time it is 0. So I am not bothered regarding that. But only we are interested in these 3 bits which will going to be used for next part of the division. Yes, remaining 3 bits. So that is why my divisor hardware will going to look like this. I hope it is clear. Last word regarding this hardware design is that regarding reminder. After performing the division operation, I will going to be left out with n minus k bits as a reminder. If the length of the divisor is n minus k plus 1 bits, I will going to be left out with n minus k bits as my reminder. So that means in our previous example where divisor was 4-bit length, my reminder's length will going to be 3 bits. So reminder will be of length 3 bits. With all these points what we observed, based on that we'll try to design our hardware circuit. So actually this hardware circuit what we will going to design will keep all the points just now what we have discussed. Based on that, say we use certain step-by-step process that can be used to simulate the division process in hardware. Okay, the first step, we assume that my reminder is initially the reminder value is 0. Okay, this is what is my first assumption. With this I'm going to start at every clock tick. Okay, because this is a hardware circuit where I need a support of a clock. Okay, so at every clock tick, okay, 1 bit of the augmented data word, 1 bit of the dividend. Augmented data word in the sense it is a 1 bit of the dividend will be used to perform the following actions. The first one is we used the leftmost bit to make a decision about the divisor. So at every clock tick, say we will look for the leftmost bit of the dividend. So during the first clock tick, this will be the one which will going to decide what should be my divisor. During the second clock tick, this will be the bit which will going to be deciding what should be the divisor. During the third clock tick, this will be the bit which will going to decide the what should be my divisor value. So like this, at every clock tick, these bits of the dividend will go to decide what should be the divisor to be used to perform XOR operation. Okay, so that means we need a circuit which will going to input these bits, say in a sequential fashion after every clock tick. When the bits of the augmented data word is inputted, so divisor gets decided, and these divisor bits will going to be XORed with the reminders. Okay, so divisor will going to be XORed with reminder to give the outcome. That outcome will going to be used for next operation. So we'll start designing the circuit as it was told to you. This will be my divisor circuit. So this is D0, this will be my D1, and this is my D2, which is all the time 0, and this is the bit which will going to come from augmented data word. So I'll do slight modification in my whole operation. Okay, so here I need one XOR circuit which will going to be XORed with this shift register block. Here too I need one more shift register, yes, to which my value will going to be XORed. And to start with I need one more XOR bit which will going to be XORed over here. This will be the hardware circuit. These are the 3 resistors which will be used to store our reminder. So as I said initially, these 3 values will going to be 0, and from here we will going to input our data word. So this is the one which will going to be inputted in a sequential fashion. By the time this bit reaches over here, this will start deciding the, say, the fates of these bits will start deciding the fates of these things. At every step these bits will going to be XORed. I'll just show you step by step, say, sequences of generation of the outcome after performing the operation. At every step what happens I will show you. Okay, what will be the, say, data word. For that I'll just do a slight modification to this figure. This is what is the actual figure we need to generate the, say, our word, our reminder. This is what is the hardware circuit, that is what we need. So this is not only the hardware circuit which will be used for generating the things. This is one of the design, one of the hardware design which is meant for generating the, say, the reminder which will going to be used in CRC. So this is what is a process. Just we'll see how exactly it will generate. Okay. To begin with, these 3 values are 0. We know if this bit is 0, this is the input to these things. So my D0 will going to be 0, my D1 is 0, my D2 is all the time 0. No need to bother regarding that. But whereas D1 and D0 are 0 because this value is right now 0, which is connected to these XORs. So during the first clock tick, this one will going to be inputted. So once this one comes over here, the value of the outcome of this XOR operation which will going to be stored over here. So that is 0 XOR 1 is what? 1. And what was during the same clock tick, that you keep it in a mind, during the same clock tick before this gets converted to 1. Okay, so since the operation is not only happening over here, so during the first clock tick the operation is happening at all the XOR gates. So the outcome is getting stored in these registers. So what happens in the first clock tick, I'll write it over here. So this gets XORed with 0, this value becomes 1. What was the previous value? It was 0. This 0 gets XORed with it. This outcome is going to be 0. This 0 was already XORed with this. This is a 0. So you see, during the first clock tick, these are the values which will going to be stored. After the first clock tick, these are the values that will going to be a part of this register. Okay, and during the second clock tick, you see that one is got inputted. During the second clock tick, now the value, what will going to be there in this register? It is not 0, it is 1. In this case it is 0, in this case it is 0. So this 0 gets XORed with this 1 during the second clock tick. Okay, sorry, now during the second clock tick, this is getting inputted. So this 0, and what is the value over here? This is 0. So this makes these two values 0, 0, and this is already 0. So now we'll start the second clock tick operation. So this 0 will going to be inputted here. This 0 gets XORed with this 0. The value that will going to come into this register will going to be a 0. So what is the value in this register during that clock tick? It is 1. and this 1 gets XORed with this 0. So if it gets XORed with the 0, this value becomes 1. This will going to be stored in this register during a second clock tick. What is the value that is stored before this value? It is 0. So this 0 gets XORed with this 0. So 0 will going to be stored over here. So after second clock tick, this is the outcome. Fine. So now 2 bits are over. Now we'll be left with 5 more bits. I'll rewrite them. Fine. Now during the third clock tick, this 0 is getting inputted. Now see what is the value stored over here after the second clock tick. It is 0. So this makes these values again 0 0 0. Yes. So with these 0 values, the operation will start. So this in the third clock tick, this 0 gets XORed with 0. So this 0 will going to be stored. This 0 is getting XORed with this 0. 0 is getting stored. This 1 is getting XORed with this 1. The 1 is stored over here. So after third clock tick, this is what is the status of these shift registers. Fine. Now we'll go for the fourth clock tick. Before going to the fourth clock tick, we need to update this value. Right now, what is the value in this register? It is 1. So this one makes these 2 bits 1 1. So this is what is the value that will going to be pulled over there. So then during the operation will start for the fourth clock tick. This 1 gets inputted. This gets XORed with this 1. It becomes 0. Now what was the value before the fourth clock tick? It is 0. This 0 gets XORed with this 1. It becomes 1. So what was the value that is before fourth clock tick? It was 0. Since this 0 gets XORed with this 0, this becomes 0. So after the fourth clock tick, this is what is the status of these 3 registers. So before going for the next clock tick, this 0 will update these values. It becomes 0 0, and this is already a 0. Then this gets inputted. This 0 is getting XORed with this 0. It is 0. Next, before the start of that, this 0 was here, so this 0 gets XORed with this. It becomes 0. This 1 is get XORed with 0 0. This is 1. Fine. So next clock tick, this 1 update these values to 1 1, and next 0 is getting inputted. This 0 will going to be XORed with this 1. This is 1, and before that clock tick, this was there. So this 0 gets XORed with this 1. It becomes 1. This 0 gets XORed with this 0. This becomes 0. I hope it is clear. During the next clock tick, this 0 will going to change these values to a 0 0. Okay. I'm going to be left out with last bit, that is 0. So this 0 now gets XORed with this 0. So this becomes 0. This 1 gets XORed with this 0. It is 1. This 1 gets XORed with this 0. It is 1. And here it stops. So all the bits gets exhausted. This is what is the final outcome of the hardware process, that is reminder. Now my reminder, what I will going to get is 1 1. So I just wanted to just show it to you. This is 1 1 0. So this is my reminder. Just compare this with paper and pencil method. There also we got the same reminder. I hope it is clear to you, this step-by-step operation. This circuit what I shown is for just the divisor what we used in our previous example. This was the divisor we used. Because of that, the circuit is designed so. Since this bit is 0, so all the time this is 0. And these two are 1. These two values will going to be decided by this bit. I hope it is clear to you. So then I will going to redraw this figure for general divisor. For general divisor case, you see, I need a XOR gates for whom the input will be from next stage. So it will be fine, and I need one more block over here whose output is going to be used over here. So like this. Sorry, it should not be over here. So for understanding reason, I'll draw one more block over here, and to which we are inputting the XOR. Fine. So this is a diagram for general one, D0, D1, and this is so on dn minus k, and this k minus 1, and this is for d minus k. I hope it is clear to you. This is the block diagram for general, and we are going to input the data word from here. The data word will be going to be inputted from that side. I hope it is clear to you. This is one of the design of this hardware. Next, we are going to discuss regarding checksum. Checksum is again one more error detecting technique. Which will be applied for messages of any length. Okay, so in internet, checksum technique is mostly used at network and transport layer rather than at data link layer. The technique what right now we have discussed, that CRC, is widely used at data link layer. So there we deal in terms of bits, so that CRC technique will be used at data link layer. And once we started discussing regarding frames, so in this subject we are going to discuss regarding the frame format of, say, IEEE 802.3 frame format we are going to discuss, and that time you will come to know where exactly this checksum will going to be placed in that frame, so which will be useful in detecting the errors of the frames. Okay, so I'll explain you during that time. Yes, but this I mean CRC, not checksum, this CRC, where exactly CRC will be placed in the frame, that time I'm going to repeat it. I'm going to tell you where exactly this CRC calculated value will going to be placed. Now we are discussing regarding checksum, which will be useful at transport layer and say network layer. However, say error detecting techniques complete without this checksum discussion. For that reason, we are going to discuss regarding this checksum. Now the steps that are involved in the checksum we are going to see, then we will take one example on checksum to know regarding how a checksum works. So in a checksum, the given message, first it gets divided into a units of m bits. So this is my message, which gets divided into a small units of m bit lengths. Okay, then these small units in turn will be used to generate the checksum. So this generator will be helpful as to calculate the checksum which will going to be appended with this message. So this is my message, the previous message what we discussed. This is message, to which again we're going to add another m bits, which will be my checksum. This is checksum, okay, which will going to be added with my message. This is what happens at the sending side. Now we'll see what exactly happens at the receiving side. Now the process that happens at the receiving side is this one. This is my message, to which a checksum is appended, which is of length m bits. Say for understanding reason I'll write it as MC, m bit checksum. You read it as m bit checksum. So which is received from the receiver, I mean sender. So this is what is the sender has sent. So the checksum has been received by the receiver, I mean the complete message along with the checksum is received. Now at receiving side, what happens, you see, they again say use these m bits of the message. Say the calculation will going to be performed on these m bits, and the m bits of the checksum will going to be used. So the outcome is m bits. Say this is, I'll call it as checker. In this checker, the outcome, these same message blocks which were used at a sending side, so those all m bits will going to be used to calculate again a checksum at a receiving side. That calculated checksum will going to be compared with the received checksum. If both are same, then the outcome will be of m bits. The message will going to be received, or otherwise it will going to be discarded. This is a decision box to accept the message or reject the message. So if it is non-zero value, then 0. If it is yes, it will be accepted. All m bits will going to be accepted as it is. This is my message. If these m bits, if they are 0, based on the checker's outcome, if it is outputting a 0, if it is 0, if it is yes, the message is correct. If it is non-zero value, it is wrong. So this wrong value will going to be discarded. So better you connect this message over here, so that this complete message will going to be received. I hope it is clear what happens at the receiving side. Received m bit message along with the checksum will be used for checking the for error. So the process that is involved at the receiving side, you see, the message which got divided into a m bit blocks, those all m bit blocks will be used in calculation of the newer checksum at a receiving side, yes, and the received checksum will be used to compare with the newly calculated checksum. If both of them they match, my m bits will going to be, the outcome of this checker is 0. That outcome is also a m bits length, it is 0. In case if these values are not matching, the newly calculated checksum and the checksum which was calculated at a sending side, if they are not matching, these m bits will going to become non-zero. So then based on that 0 or non-zero value, decision will be done whether to accept this message or to discard this message. One more important thing regarding this checksum is that we are going to use ones complement addition. So this ones complement arithmetic will be useful to handle the messages of length m bits. Since there is a addition involved in this checksum calculation, if I add say n m bit messages, there is a possibility that I may get my outcome which is more than m bits, In that case, it's my job, it's our job is to keep the outcome to a m bit value. So to keep the outcome to a m bit value, we are using this ones complement addition. Say what exactly happens in the ones complement addition is, say if number has more than m bits, the extra leftmost bits will be used to add to these rightmost m bits. Fine. So this technique we call it as wrapping. So if whatever the additional bits that will going to be generated, they will be added back to these m bits. So that I'll just show it to you by taking one example. So while calculating the checksum itself, whatever the example we use, so we'll take such an example that should generate more than m bits, and I'll demonstrate that how exactly that, say, wrapping will going to happen. Consider one example in which my message is get divided into a 4-bit number. So I have a message blocks m1, m2 up to m5, and length of each message block is 4 bits. Length of each message block is 4 bits. So with this assumption, I'll take 4 numbers and I'll perform the calculation to find the checksum. So let us take those 4 numbers. So I'll express them in decimal for easy understanding reasons. So this is 7, 11. This is my length of my second message block. My third, it is 12, and fourth is 0, and the fifth is 6. So this is my message which got divided into a 4-bit block. So look at these numbers what I have selected, all of them are within 4 bits. Okay, no value is greater than 15. So that means all these messages are of 4-bit length. I hope it is clear. So let us perform the calculation of finding the checksum. Okay, so as per the checksum calculation, we